Hello, this is Mr. Waters. I'm providing an answer to someone emailed me, question someone emailed me about number 7. Okay? And so here is number 7 here from the book, number 7 on the homework. And I'll zoom in quickly on it. It says for, there it is, time t in hours from 0 to 1, a bug is crawling at a velocity v in meters per hour given by that thing right there. Using delta t is equal to 0.2 to estimate the distance that the bug crawls during this hour, find an overestimate and an underestimate, then average the two to get a new estimate, right? Now, yeah, that's a little weird, right? It's different because they give this rational function, which is always, a little bit more challenging to work with. And then they give this delta t, which is 0.2, right? So how does that work? Well, really, it's not any different than the 0 to 6, and the delta t equals to just 2.0 up here. We can work about it. We can work it through the same way. Now, what I'm going to do is, let me zoom back out again. Put that aside, and you can consult your own book if you want to continue to look at the problem. Let me get this centered back on the work here. Okay, so here's the function equation, 1 over 1 plus t, v, equals that. There's the interval from 0 to 1 hour. There's the delta t. Now we could go ahead and use use the formulas that we've been working with, right? And we said, here's one we used in several other problems, that delta t, that is this, and remember delta t is the width of each of the intervals. However many there are, which they didn't tell us, we know that each one is supposed to be 0.2. Now one way to do it would be to use this little formula here, that delta t is equal to whatever the ending number of the time interval is, that's 1, minus the beginning of the time interval, in this case that's 0, divided by whatever n is. Well, we don't know n. We don't know n. That's what we'd like to maybe know, right? So, turns out we could reformulate this, switch the n and the delta t, so that n, which is the n minus the beginning, divided by delta t. Now, I worked this out, but we'll come back to that in a minute. We kind of don't even need to do this if we really understand what's going on here. We look here, and we see, the interval is from 0 to 1, and each interval, which are going to be even in width, are supposed to be 0.2 wide. Well, okay, so we go down to the graph here. I made out a graph, and we start out with the idea that, okay, the first interval, each interval's got to be 0.2. So we go from 0 to 0.2, right? And then another 0.2, which would take us to 0.4, and another 0.2, which would take us to 0.6, and another 0.6, which would take 0.2, which would take us to 0.8, and another 0.2, which would take us to 1.0. And that works out neatly what we would get over here if we employ this formula, right? Because we see here that there are 1, 2, 3, 4, 5 intervals with 0.2, 0.4, 0.6, 0.8, and 1.0 as the boundaries, right? And 0 as a boundary as well. So here, 1, so there's 1, 2, 3, 4, 5 intervals. 1 minus 0 is 1 divided by 0.2. Oh yes, our little formula tells us that there would have to be 5 intervals. Now what we would do is we would plot the function. And here is t, and this is the function 1 over 1 plus t, and to plot these, we're going to go ahead and make up a data table using each of those values there. So 0, 0.2, 0.4, 0.6, 0.8, and then 1.0, and then using a calculator, all right, we just kind of plunk those numbers in to see what we get, and I'm searching for my calculator, which is, okay, I guess we'll just use this one here, okay? So this is 1 divided by 1. Okay, 1 divided by 1 plus 0, of course, works out to be 1, right? If I add 0.2 in there, that's 1 plus 0.2, so that's 1 divided by 1.2. I'm getting 0.83, right? And then put 0.4 there, so it's 1 divided by 1.4. That's 0.71, right? And then put 0.6 there, 1 divided by 1.6. That's 0.63, rounded off, right? And then 1 divided, put 0.8 there. So it's 1 divided by 1.8. That's 0.56. And then we put 1 there. 1 divided by 2 is 0.5, right? So now we're going to use those. We can, roughly graph those over here, but we're going to use these like we did on our table problems as the boundaries as the heights of the rectangles. So this will be 1, so that'll be 0.5, so 1, 0.5, right? So it's 0. I'll use a different color here. So hopefully, okay, because the question is really about what do we do with the 0.2, but I might as well take it a little bit further here. 0, we graph that, right? Oh, you know what? I think I'll use this color here. Right? So 0, 1, and then 0.2 is about 0.83, which might be there, right? And 0.4 is about 0.71, which might be there. And 0.6 about 0.63, a little bit lower. 0.56, a little bit lower. And then 0.5 right there. Now, if you graph this function on your graphing calculator, you should get something between 0 and 1 that looks like that, right? Okay, so here is our there's our function, our speed function for the bug, and we want to estimate, that distance there. The area under this curve will give us the distance that the bug has traveled. And so they want the upper and the lower estimate. Well, for a decreasing function like this, we're going to go ahead and use like this. All right, the right hand rectangles, and I didn't even mark off the boundaries, but I suppose I should. These are the boundaries, right? And so for a decreasing function like this, you can see that the right-hand boundary is anchored on the right, because that gives us rectangles that are underneath. It's going to give us the underestimate, right? Like this. Right? And then we use these values here. That's why I wasn't worried about graphing them exactly on the graph, because they give us what the values are supposed to be. So this would be, since we're doing the right-hand sum here, the right-hand sum is going to give us the underestimate for this decreasing function. So that is 0.83, 0.71, 0.63, 0.56, and then 0.5, just like that, right? And then the delta t for each of these, of course, is 0.2. So that's a decimal, but we still find the area the same way, right? Okay, so the area of this is going to be, the first rect one is 0.8, 0.2 times 0.83, then 0.2 times 0.71, then 0.2 times 0.63, then 0.2 times 0.56, and then 0.2 times 0.5. And then Mr. Calculator works that all out, right? 0.2 times 0.83, 0.166, okay, 0.2 times 0.74, and that is going to be 0.148. Oopsie. It's 0.2 times 0.71 is what we want, so it's 0.142. Okay, 0.63, that's 0.126, right? And then this one is 1.12, and then of course that's 0.10, right? And then we add them all up, right? 0.166 plus 0.142 plus 0.126 plus 0.112 plus 0.1, and that is 0.646. So that's the underestimate here, is the 0.646. Then you would go back, and I think I won't do the rest of it here because I think this starts to become just like the other ones. All right, now you would go back and you would find the overestimate by doing the left-hand sums, right? So here, to find the left-hand sums, we would start, because the left-hand sums for this decreasing function here, let's make sure we can still see the function. Just like that. Okay. The left-hand sum would give us the overestimate, which are represented by these rectangles right here, and we would use the same values, but notice that the decreasing function, they're going to be anchored on the left, so we would use 1, 0.83, 0.71, 0.63, and 0.56 for the heights of the rectangles, but then still use 0.2, right? Whatever that number comes out to be, it'll be bigger than 0.646. To get the average, you'd add them together and divide by 2, and that presumably, the number, the value that's halfway between those, would be a closer estimate of what the upper and the lower are. Okay? All right. Hope this helps. And I will post this at the top of Canvas, and you can look for it at the very top of the module on Canvas, and it'll say homework help number 7.